All right, let's get into it. We're going to talk about what might be one of the biggest blind spots in our AI stacks right now. We're all so focused on crafting the perfect prompt and tweaking our models, but there's this critical vulnerability that we really need to tackle head-on: insecure output handling.
I mean, we all had this drilled into our heads from day one, right? Never trust user input. It's practically the first commandment of writing secure code. It's the whole reason we validate, sanitize, and parameterize literally everything that comes in from the outside world.
But here's the crazy twist with generative AI. What happens when the most unpredictable and, frankly, the most dangerous data isn't coming from some user's form, but from the very model that we've baked into the core of our product? That's the huge paradigm shift we're all facing.
So yeah, we have to shift our focus. It's time to look beyond just the input and really understand the output threat.
This means we have to expand that old security role. The new mantra, the one we have to live by, is this: never trust data being sent to an interpreter. And I mean any interpreter: a web browser, a server's command line, a database, even another API. If some component downstream is going to execute or render data, you have to assume that data is hostile, period.
So let's put a proper name on it: insecure output handling. At its core, it's just the failure to treat the data that's leaving our app with the same level of suspicion as the data that's entering it. We take some data, maybe from a user, maybe from an LLM, we process it, and then we just pass it along, assuming it's safe now. That assumption right there is where things go wrong.
And here's a really critical distinction. Insecure input handling, think preventing SQL injection, that's all about protecting our own server from bad user data. We're defending our own house. But insecure output handling is different. That's about protecting the next system down the line, usually the end user's browser, from the output we create. We're making sure we don't accidentally send a bomb out the door to somebody else.
Now you might be thinking, okay, this isn't a totally new concept. And you'd be right. But what you're about to see is how LLMs completely change the game and just crank the stakes up to 11.
Here's the heart of the problem. Our code is deterministic. You give it input A, you get output B, every single time. An LLM is not that, at all. Its output is probabilistic. It's basically making a very, very educated guess based on patterns. Trusting its output to be safe by default is like expecting a coin flip to land on heads every time. It's just a fundamentally flawed assumption.
And of course, that unpredictability can be turned into a weapon. The main attack vector here is prompt injection. And this is so serious that OWASP has flagged it as the #1 risk for LLM applications. An attacker isn't finding a bug in our code. They're essentially socially engineering our model, tricking it into becoming an accomplice and generating a malicious payload for them.
So let's trace the attack. It's a pretty simple chain of events. Step 1, the attacker writes a really clever malicious prompt. Step 2, our LLM, trying to be helpful, does exactly what it's told and spits out a payload, say a nasty piece of JavaScript. Step 3, and this is our failure point. Our application blindly trusts that output and injects it straight into the HTML. And boom, Step 4. The user's browser sees the script, assumes it's legit, and executes it. Game over.
And the consequences? Oh, they're all the greatest hits of application security nightmares. On the client side, you've got cross-site scripting, which leads to things like session hijacking and account takeovers. If that LLM output is being fed into a backend system, now you're talking about server-side code injection, like remote code execution or SQL injection. And, of course, there's always the risk of just tricking the model into leaking sensitive data it shouldn't be sharing.
Look, this isn't just a theoretical problem. Let's look at some hard data, because it really drives home just how critical this is right now.
So the #1 result of this failure is cross-site scripting. And according to the 2024 CWE Top 25 list, XSS isn't just a problem. It is the single most dangerous software weakness in the industry. #1. Let that sink in. We are building systems that can potentially become factories for the industry's top-rated threat. And the financial impact is just staggering. In 2024, the average cost of a data breach hit an all-time high. You can see it right here. We're talking almost $5 million per incident. This is the kind of metric that gets C-level attention, and it's a direct line from the code we write to the company's bottom line.
And we're not talking about small companies making rookie mistakes here. British Airways had payment data for 380,000 customers stolen by an XSS-based card skimmer. Fortnite exposed 200 million player accounts because of an XSS flaw. These are huge, high-profile examples of what happens when you don't handle output securely.
Okay, enough doom and gloom. The threat is clear, it's real, so what's our playbook? Let's talk about defense.
Okay, our single most important technical defense is context-aware output encoding. The keyword here is context. How you sanitize data depends entirely on where you're putting it. If data is going inside an HTML tag, like a div, it needs HTML entity encoding so a script tag can't fire. But if it's going into an HTML attribute, like an href, that requires attribute encoding. And data inside a script block, that needs JavaScript encoding. Using the wrong one is just as bad as using none at all. You have to be precise.
Now, encoding is our first line of defense, but we need defense in depth. That means also having strong allow list-based input validation to stop bad stuff from even getting in. For those cases where you actually want the LLM to generate rich content like bold text or lists, you use a battle-tested sanitization library like DOM Purify. And finally, your last line of defense, your safety net, is a strict content security policy. A CSP is a direct order to the browser telling it exactly which scripts are allowed to run so it can block malicious ones even if they get injected.
All right, let's bring this all home. Here's a practical, no-nonsense checklist for taming your LLM outputs.
Here are 3 non-negotiables for any LLM integration. 1. Strict output validation. Define a rigid schema like a specific JSON structure for what the model's output should look like, and you reject anything that doesn't conform. That stops malformed payloads cold. 2. Sandboxed execution. If your feature runs code that the LLM generates, that code must run in a temporary, isolated sandbox with zero access to your network or file system. No exceptions. And 3. Human-in-the-loop review. For any high-risk action, deleting data, sending money, deploying code, an actual human has to give the final OK. Don't let the model make those calls unsupervised.
So I'll leave you with this final question. The output from your LLM, it's not your data. It's not trusted. It's untrusted, unpredictable input that just happens to be arriving in the middle of your application. The real question is, are you actually treating it that way?